Hey there, 2200. Today I'm going to help you with your activity. Now, I've never made a video for an activity before, so hopefully this goes smooth. In fact, the biggest challenge I think is going to be me keeping my mouth shut. So this is what I plan on doing, using my hands to just manipulate things around. I will read your tutorial and pretend as if I'm the student, and I'll just be an extra set of hands for you and do the things they ask so that you can properly answer or address the questions posed to you in that tutorial workbook. So with that said, let's get started, and I think we'll, for the most part, do it on the floor. I need a bird's eye view of what's going on, so the way the camera is mounted, and it'll just be easier to probably just do it on the floor. So hopefully, well, let's get started. Okay, see you in a minute. Okay, students, let's get started here. What we have on the floor are an assortment of different objects, and I am looking at your workbook, page 113, magnets and magnetic fields. So, 1, magnetic fields. A, investigate the objects that you have been given. Separate the objects into 3 classes based on their interactions with each other. So, what we'll do is investigate how they interact with each other, and what we'll do first is well, let's go over what we have. This here is a cork. Obviously, this here is some change. We have 2 machine screws. As a heads up, one of them is steel and another one is stainless steel. I mention this because some stainless steel objects are not magnetic, and that just has to do with the manufacturing process. We have a couple of washers. There's a tiny one here. I'm not sure what this is made of. I know this one here is brass. Here's a piece of plastic. It's just, you use it to fix cable to a wall. This is wood. Now, I have a bunch of different types of wood in here. Pine, maple, oak, poplar. But in the interest of time, we're just going to use this wooden dowel because they're all going to behave the same way. So this will be representative of our family of wood products. Paper clip. A couple of magnets, and this here is an inductor. Now, you may not know what an inductor is, but for the purposes of this activity, an inductor is simply copper wire wound around in a circle there. And by the way, so it's wound around this plastic piece here. This plastic piece will play absolutely no role in any effects you observe from this inductor. That is just to help get this wire in that wound up pattern, and then of course they leave it there so it's mechanically stable, it doesn't get smashed or anything. But I mentioned that because when you list this under your objects, you can just list it, well, I guess you could list it as an inductor or simply wound copper wire. So that's our wound copper wire. And let's get started. So I will get these objects out of the way and maybe zoom in on a few at a time. Now, there's our change. This is almost pointless because as you intuitively know, everyone's had change in their pocket. They do not interact with each other, right? Yeah. Okay. Let's see. These 2 washers, they're made of different material. One of them is brass. The other one, I'm not exactly sure what it's made of, but they don't interact with each other either. By the way, neither do the washers interact with the coins. So if you were doing this in person, I guess what I'm trying to say is I'll let you know if there is any interaction between these objects, like if there's a slight pull or push or whatever. I would have to be the one to tell you since you're not here in person. But nevertheless, and as you suspect, there is absolutely no interaction going on between the change and these washers. Now, if we throw in a few more items, we have some more metal, we have the wood and the plastic. None of this stuff interacts with each other. well, technically, gravity is this piece and this piece are attracted to each other with gravity as well as all the others, right? But hey, that's not the point of this class, nor do we have any equipment in this garage to detect what that attraction is. It's pretty much non-existent, right? It's so weak. But okay, I digress. We are focusing on other types of interactions, and with that said, none of this stuff is interacting with each other. We could throw in the cork, same thing. And that right there is a washer made of rubber. Now, nothing interesting is happening, so let's get these bar magnets involved. And I will place, let me zoom out. I will place one there and mess around with the cork. The cork is rolling to the north. That's just because of the slope of these tiles. There's no interaction with the magnet and the cork. The wood, as you would suspect, there is no interaction between the magnet and the wood as well. And we have this machine screw. Okay, our first interaction. That screw is indeed attracted to this side of the magnet, and it is made of steel. Question is, would it be attracted to the middle? Very slightly. What about the other side of the magnet? Now we know it was attracted to this side. Would it be attracted to this side, or would it be repelled? Okay. That answers our question. It is attracted. It is attracted to both sides of this bar magnet. And let me pry it out. Paper clip. Same phenomena. It is attracted to both sides. Weakly attracted to the center as well. This little guy, this washer, let's see. It is strongly attracted to the north side and strongly attracted, did you see that? It is strongly attracted to the north side. Did I call this north? Well, you know it's south. It's labeled there. What about this guy, the brass washer? Nope, not at all. And I'll convince you. Well, you see it. North side, nothing. Plastic, need I go through all these things? We already know, right? Okay, plastic, nothing. Rubber, nothing. What was this? Our other machine screw. Now it is rolling towards the south side of this magnet. It wasn't attracted to it. This is stainless steel. So this stainless steel screw is not this magnet is having no effect on that stainless steel screw. I'm almost butting this magnet up right to the head of that screw, and it is doing nothing. Well, now it's touching it because I pushed it into it. What about the north side? Nothing. Nothing at all. There's a gap of a few hairs in between that screw and the north side, and it is not sticking to it. So it's not affected by the magnet. And what else do we have? Oh, our last thing. Yeah, that was like the first thing I did, right? Our inductor. Let's see what type of effect this inductor has, or what type of interaction occurs between this inductor or wound copper wire and our magnet. So it's sticking to it. Now, you know what? There is okay, I lied. I initially said that this core spool was made of plastic. It is made of metal. So I know that the copper isn't being attracted to the magnet, it's the spool. So let's see. We will examine that inductor further momentarily. Two magnets. Let me zoom out. So we have two magnets here. How do they interact with each other? Let's see. This magnet seems to produce a torque on that one. They attract each other. But wait a minute, what if I turn this one around? Repels it. Same thing with this side. What would your guess be? I have, well, let's not talk about poles. Let's just see what happens. So there's an attraction there, and it repulses it there. Now, does it only produce a torque, or if I lined it up in such a way where this wasn't allowed to spin, would it actually push it? That's the question. And what we'll do is use this little track. It's just a piece of wood with a couple of rails on it. We'll stick one magnet there. We'll get these two sides lined up, and you could see it pushes it. Of course, if I put this end of the magnet there, it wouldn't push it. It would stick together. But if I flip it, it pushes it. So that should give us all the information we need to start filling out that chart. Oh, that's right. So let me talk about the classes, the three different classes for just a moment. Now, you might be inclined to call one of your classes magnets, but to me that doesn't sound right, because if you look at number 4, it says, to which class do magnets belong? If this class 1 was magnets, well, the answer to this, which class do magnets belong? Well, the class of magnets. That doesn't sound right to my ears. Let's be more general. What could we call class 1? How about objects that produce a magnetic field? So also, so that you don't only have one item in class 1, if class 1 was indeed items that create magnetic fields, we are now going to examine this inductor or wound copper wire. And of course, class 2 could be called, let's see, what do we want to call it? Like objects that interact with the magnetic field. How about that? We don't want to call it metals, right? I mean, that's too general, because as you've seen, we have different metals that interact differently with magnetic fields. So how about class 2 is objects that interact with the field. So let me put you on pause, and we will further examine that inductor. Okay, so there is our inductor, and again, that is nothing more than some copper wire wound around a metal spool or core. And I have this tiny washer here that already exhibited the property that it interacts with a magnetic field, and I have it next to that inductor. Now, nothing's happening. There's no interaction between the two, as you might suspect, right? Why would there be? That inductor is nothing more than just, some metal components, the wire and the spool. But what if I ran a current through it? So I'm going to go ahead and turn this on and put this washer close to it, and you could see that it's stuck to it. Or can you? Let me zoom in there. That washer is indeed stuck to the end of that inductor. Now, with my right hand, I'm going to shut off the current. 1, 2, 3. I shut off the current, and the washer is no longer stuck to that inductor. Let me turn it back on. it's stuck to it. And let me zoom out and turn this off, and the washer falls. So essentially this, well, I won't say anymore. I'm just going through the motions. Let's see. What I'll do now is get a compass and put it right in front of that inductor. And right now I'm trying to get rid of the magnets around that are placed around me so that this points north. Let's see. I want to put this right there in the east direction. So technically this should go in this orientation, right? Nah, it doesn't matter. I am going to turn on our current. Here we go. Turn it off. Turn it on. Okay, so when I turn on a current, this needle points towards that inductor. What would happen, do you suppose, if I put the compass here? Would that needle point to that inductor? I think I called it a conductor. Well, let's see what happens. Sorry, you were out of frame. Let's see what happens when I turn on the current now. Will this needle point to that inductor? No, it doesn't. It points in the opposite direction. By the way, let's see. Let me get a... Let me zoom out and get a magnet. The needle is pointed towards that bar magnet, the needle of this compass. But if I move the compass on the other side of the bar magnet, now the needle points in the opposite direction of that bar magnet. I just wanted to do that to illustrate that that inductor seemed to have created a magnetic field that mimics a bar magnet. So actually, if I was to run a current through an arbitrarily shaped wire, it would indeed produce a magnetic field, but it would not resemble that of a bar magnet. Our inductor here coincidentally produced a field just as a bar magnet does, but that's simply because of the geometry of that inductor. In other words, how it's wound. You'll get into that further on in the semester. But anyway, there are our observations on how these different items interact, and that should give you enough information to do fill out that table. And I'll put you on pause so we can get on to the next one. Okay, this section here is for part B. Now, permanent magnet, not a permanent magnet, but let's say we didn't know that. We had no idea. For instance, both objects, this wasn't marked north or south, both objects were identical in size and shape. What I can do is touch this piece of metal up against this, and there's a pretty strong, well, let me do it this way first. There's a strong attraction, strong attraction, strong attraction, strong attraction. Anywhere I place this tip on this object, I get the same force of attraction. Same with the other side. It's the same force. But it doesn't quite work the other way around. In other words, if I touch this object to different parts of this object, the force of attraction is different. So it's pretty strong there. Same strength there, but it's weaker there, and yet weaker there. And in fact here, there's nothing. Let me start going out. I feel a little bit but it's still weak. And then of course, when you get to the end, it's pretty strong. So strong I could lift up this magnet, and it's pretty heavy. So that should be enough info to determine a method for determining which item is the actual magnet. Okay, I'll put you on pause so we can get on to the next part. So this here is for part C. Just like part B, where we determined which item is the magnet, you could determine how many poles an actual magnet has. And that's pretty straightforward. You would just test the magnet with a object that interacts with it and find how many points on that magnet are interact with the object strongly. And if you do this with whatever magnet you'll find, you'll notice that there are only two of such points. I'm not going to go into addressing the other two questions because that would just be me doing it for you. You have enough information to answer those yourself, although you'll need to be a bit clever on answering number 3. Using 3 magnets, find a way to distinguish one type of pole from another. Think about that. Come up with the solution. All right, let me put you on pause. Okay, ladies and gentlemen, we are now on to part D. And if you're wondering why I'm on the floor, we're going to shoot this on the floor because part E definitely needs to be shot on the floor. I need to give you like an overhead view of what we're doing. So anyway, with that, describe how an uncharged pith ball suspended from a string can be used to test whether an object is charged. Then predict what will happen when an uncharged pith ball is brought near one of the poles of the magnet. Explain. So go ahead and do that, and then put me on pause, then do that and come back. So put me on pause. Okay, you're back. Let's go ahead and do that. Okay, ladies and gentlemen, here is our uncharged pith ball. Now, if I was to bring a charged object near this pith ball, that pith ball would be attracted to it, but that's not news to us, right? You've already gone over this, and hopefully you remember and understand why that would happen. What we're going to do is, by the way, there's much more I want to say about this, but I'm doing my best to keep my mouth shut. What we want to do is test this with a pole of a magnet. Now, I'm going to use this magnet here. It is much smaller than the other ones that we were using, but I want to use this one because it is like 10 times stronger than this one here. By the way, the poles of this magnet are on the long side. The poles of this little magnet are on the opposite ends of the smaller width side, FYI. And here is one of our magnetic set screws. You could see that this is indeed a strong magnet. So, uncharged pith ball, one of the poles of the magnet. I bring it close to this pith ball and nothing. Let me put it on the other end. Nothing. So, go ahead and answer that next question and put me on pause. Okay, let's test your prediction about bringing the other pole near this pith ball. I don't remember which pole I used last time, so I'll just test both of them out. So this is one pole of the magnet, and it is not doing anything to that pith ball. Now I'll flip it and bring the other end, and nothing at all. Let's get on to the next part. Okay, now we are on to part E. A paper clip is attached to a string and suspended from a straw. Well, technically it's suspended from that wooden dowel there, but nevertheless it is placed so that it hangs inside of an aluminum foil lined cup as shown. So let's see, let me zoom in a bit. That paper clip is kind of hard to see with the bottom of the cup there lined with foil. Maybe I should have shot the paper clip with some red paint, but nevertheless I think you could make out if it's moving or not. It's on the end there of that white thread. As a side note, not only is the bottom of that cup lined with aluminum, but all the sides are as well. And what you do now is put me on pause, read number 1, make the prediction that they ask you to do, and we'll test it when I get back. So put me on pause. Okay, I'm back. Now let's test out your prediction. I have a charging rod in my hand and I'm going to charge it and see what effect it has on that paper clip. None. Okay, I'll put you on pause so that you can make the next prediction and we'll test that out then. Put me on pause. So now, predict what you would observe if the paper clip were outside the cup. Explain your reasoning, then check your prediction. So go ahead, put me on pause and do that, then get right back to me and we'll go ahead and test it out. Okay, pause. Unpause, I'm back. Now, I have a charging rod. Charge it up. Let me zoom in on that paper clip. And what I won't do is bring this charging rod any closer than I did when the cup was there. So you can see it definitely affects the paper clip. All right, let me put that paper clip back in the cup and test it out with a magnet as per E number 2. I'll put you on pause. So there's the paper clip inside of the aluminum foil lined cup. As you recall, when I moved the charging rod charged near this, it didn't have any effect on the paper clip. We're going to see what effect, if any, the magnet has. And I know it's still moving, but that doesn't matter, and you'll see why. So here's my magnet, and I'll bring it close to that paper clip. And obviously, it feels it. So now we are at the part of magnetic fields, part 2, 2A. Obtain a compass from a tutorial instructor. Use the compass to explore the region around a bar magnet. Okay. Now, what you can do is simply put this on pause if you want to make any recordings, but I'm going to move this around for you as if you were doing it yourself in the classroom and make any observations that you care to note. One comment is the needle of that compass is not moving like willy-nilly, right? It's moving purposefully. Although it's changing direction, it is steady. It's not just swirling about its swivel point. So with by pressing pause at any moment in this segment of the video, you can make you could record your data. Now I'm going to even spin this a bit, spin the compass. You can see how the needle remains the same as far as how it's oriented. All right, there you go. Okay, this part of the video will allow you to address A number 2. So what I've done was removed all other metal objects away from this compass, and what we're going to do is shake it up and see what it does. Now, instead of just shaking it up, I can do something better than that. I'll get a magnet and kind of spin it around like this, and then see what happens to it. Of course, right now I have the magnet far removed from the compass, and I guess they would like you to make note of what it's doing. By the way, okay, so maybe it could have just landed in that position, right? It could have been arbitrary. What I'll do is I'll spin it around again, move this magnet far away from the compass. What the hell? I'll do it one more time. Move the magnet far away from the compass. And there you go. With that info, you should be able to answer that question. I'll put you on pause so we can get on to the next one. So moving right along to question 3, let's see. The second sentence asks you a question. No need for a demonstration there. The third sentence is use your compass to identify the north pole of an unmarked bar magnet. Okay, we'll go ahead and do that. There is our compass. It is placed facing north, and I will put an unmarked bar magnet here. Now, this bar magnet has a pole on its left side and its right side, and what you are to do is indicate which side of the magnet has its north pole, the right or left side. And you can do that by the orientation of this compass. Let me get it out of the red tile there. So I'll move this around, and that will give you enough information to answer that question. Which side is north? There you go. Okay guys, we're now on part B. So what I went ahead and did was just drew this but larger. So I can place a magnet on our diagram there, and we can draw out the direction of our magnetic field. So put me on pause, read that part if you haven't done so yet. Otherwise, let's get to it. Let's see, place a compass at each of the lettered points in the enlargement and draw an arrow to show the direction in which the north end of the compass points. So I have a compass here, and it is pointing due north. Obviously, there's no metal or objects around it or magnets. Let me go ahead and put this on point A. So the pivot point of that compass is on A, and I'm going to introduce the magnet. Now, this magnet is a small one. It broke, so you can't see the S there, but this is indeed the South Pole. Let me put it here. And you could see where the needle points now. It shifted. So as I move this around, in the interest of time, just go ahead and press pause and make note. So here we go. It is at point B now. Now I will move it to point C. And now point D. And now point E. And there you go, we're finished. Devise a method by which you can determine the approximate relative magnitudes of the magnetic field at each of the marked locations. Explain your reasoning. Well, that's pretty simple actually if you think about it. Here's my magnet, and we want to know, say, the field there versus here. When I say field, I mean field strength, or the field there versus farther away. And here's, well, I won't say how to do it, but I'll give you a hint on how I would do it. I have a larger magnet here, and I will put it so that it changes the direction of the compass. Then I'll remove it and observe how the compass now shifts direction due solely to that magnet. Now I can move it out further, disrupt the compass with this larger magnet, move it, and see how it shifts again. In other words, if it took, I know this is going to be out of frame, if I have it much farther away and I remove the magnet, you could see the needle moves to its new location much slower. So I'll just leave you with that. Now on to part C. I'll put you on pause. So after you've answered question number 2 for part B, we can move on to part C. Here's part C. Essentially, we're doing the same thing except with these small little magnets. Actually, I'm stacking them together. I have 12 of them, and I'm going to place them on this diagram here. And hopefully this doesn't roll away while we're doing this. So first thing I'm going to do is place our compass at position A. There we go. And again, you could pause this if you like whenever I move to a new position so you can make note of it. There it is at B. There it is at C. There it is at D. And last, there it is at E. All right, I'll put you on pause and we'll get on to the next part. Okay, on to part C2. Here's my magnet. I'll set it down at an arbitrary position. And here's my compass. I'll move it around a bit. And obviously, as we've already seen, there are only 2 poles associated with this stack of magnets. We will break it in half. So we have 2 stacks of equal length. Doesn't matter. Okay, now let's see how many. Let me move this one up further. Actually, I'll get it off the red because then we can't see the compass. How many poles are associated with this magnet here? I won't answer that for you. I'll just move this around so you can tell. Then I'll move it around to this guy. So you have a good idea of what the field looks like in this whole region here. And you should be able to address the question as to how many poles exist now. I'll put you on pause so we can get on to the next part. So now we are on to C3. This diagram here that you have in your tutorial was copied onto this piece of paper. I got my half stack and put it on the right hand side, and what you are to do is determine the field created by that half stack there on the right side. So if I find my compass, just give me a second here, okay? I will put it on the dot marked A. So there we go, that's A, and again, just press pause if you want more time to record this. That was A, that there is B, that there is C, that there is D. Let me check my camera and see what you are viewing. Okay, good enough. And that there is E. Now we need F. Uh-oh, that's going to be pretty hard. Obviously, I can't get this pivot point right on F, so I'll just put it as close as I can to it, which would be right there. So actually, the point F, the direction of the field at point F would be the same here, 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 right? I mean, you should have figured that out by now. The farther you get, well, I'm not going to say anything. But anyway, that is the direction of the field at point F. So that is part of part C3. The other part now is to do the left-hand side. So you're going to draw vectors again, but now with the magnet on this side at those same points, of course in a different colored pen. So there we go at A, B, C, D, E, and that will be our point F right there. This is rolling downward, so it's shifting that a bit, but that is our point F. And there you go. Let me put you on pause, take a look, and see what else we need to do. Oh, okay, I spoke too soon. Oh, that's it, ladies and gentlemen. Feels good to lay down. We are finished. That's it. See you next week. No, I won't. I don't do 2200 activities. Actually, for those of you who have me in a lab where the instructor has you watching my videos for the experiments, see you next week.